So, in the previous lecture, we looked at the method of images as a way of analyzing bounded flows, and we also looked at the Blas's theorem. So, today what I want to do is to use some of these concepts, especially the Blas's theorem, and we would show that how we can use this theorem for calculation of force over a body which is immersed in this flow, and we will do this specifically for flow past a cylinder with circulation. Which would mean that gamma will not be 0 in this case, and we will do it in two ways. One would be the more classical approach, which is by calculating or integrating the pressure distribution over the surface of the cylinder. The second approach, which will be using the Blas's theorem, and thus by the end of this lecture, hopefully you will be able to understand how the Blas's theorem comes in very handy, and you will understand the utility of the Blas's theorem, how powerful it is in deriving these solutions or calculating these forces. So, let us start with the old problem now, which is flow past a cylinder. And this time, as I said, we are doing this with circulation. All right. So, we started this problem in lecture 8, in case you want to refer back to the videos, but in somewhere around lecture 8 we started this discussion. And what we discussed in this problem is that this is a flow which is formed by superposition of 3 elementary flows. We have a uniform flow, then we have a doublet, and finally we have a free vortex. So, these 3 elementary flows when combined gave us flow past a cylinder. So, we had, as I said, uniform flow. So, u is the velocity. We had a doublet centered at the origin. So, this is a doublet which had some kind of a flow feature that we have seen now. All right, and then we also had a free vortex, but this was a very special free vortex. This was a free vortex which had a clockwise circulation. So, we had a free vortex which was also centered at the origin, but with a clockwise circulation. So, I can say this is clockwise circulation. The strength of it was gamma. Doublet we could write as mu, and of course, u is given. So, when we added these 3, we got the flow past a cylinder. Now, you also might remember mu was u a square and a was the radius of the cylinder for which this flow is applicable. For this flow, we found that the velocity component u r comes out as u 1 minus a square by r square cosine theta, and u theta is minus u 1 plus a square by r square sin theta minus gamma by 2 pi r. Okay, these were the velocity components. In general, recall that the flow field looks something of this type, that we have stagnation point, okay, where the flow happens in this fashion. Okay. But what I am saying is that the flow field, the velocity vector around the cylinder can be given by these components u r and u theta. Now, to calculate force on this cylinder, as I said, we will do two methods. One is integration of the pressure over the cylinder, that would give us a force on this object. What I need to do is to calculate first the pressure distribution. So, to calculate the pressure distribution, let us first derive the velocity variation on the surface of the cylinder. Note that this cylinder has a radius a. So, on r equal to a, which would become any point on the surface of the cylinder, u r, as you can see, will be 0, right, if you put r equal to a in that function, and u theta will come out to be minus 2 u sin theta minus gamma by 2 pi a. That is the velocity or the two components of velocity on the surface of the cylinder. I can also apply Bernoulli's equation now to be able to write the pressure distribution from the information about the velocity. What I mean by that is, we can say that if P naught is a pressure far field and we already know that the velocity is capital U, so half rho u square is a dynamic pressure. This should be pressure on r equal to a as a function of theta plus half rho, say u r at r equal to a square plus we can say u theta square on r equal to a, right. I know that u r on r equal to a is 0, so I need not worry about this term, but basically I can use this now to derive what pressure would be on the surface of the cylinder, which would be P naught plus half rho u square minus half rho u theta square on r equal to a, and we can use that function there to write this as P naught plus half rho u square. We can bring, let us say, this function here into here, okay, and we can write that this would be minus half rho, we will have a minus 2 u sin theta minus gamma by 2 pi a square. So, we can sort of simplify this a little bit, open up our brackets and maybe take like terms together. So, what we will get is P naught plus half rho u square, we will have a minus 1 by 2 rho 4 u square sin square theta, then we will have minus half rho gamma square by 4 pi square a square, and then we will have minus half rho times 2 u sin theta times gamma by 2 pi a into 2, okay, which would give us, well, we can look at, there is a rho u square term common here. So, I could maybe combine this as P naught plus half rho u square 1 minus 4 sin square theta. We have an additional term which is minus 1 by 8 rho gamma square by pi square a square, and then finally, we have a 2 cancelling here and 2 may be cancelling there. So, we will have rho u gamma sin theta by pi a. Okay. This is P r a comma theta, and this is an important result that we would need. Okay. Say this is equation 1 for now. So, you can recall, remember when we looked at pressure distribution over a cylinder, circular cylinder without circulation, we only had the first two terms, and we even looked at how this pressure varies as a function of theta. Clearly, the solution that we have also makes sense, because if you put gamma to be 0, if there was no circulation, we would revert back to the same solution for pressure which we got for a cylinder without circulation. So, It is a good way of verifying whether we are on the right track. At least gamma 0 gives us the same pressure distribution. Okay. Now, before we move further, let me talk about how we would get force on this cylinder. So, say we have this cylinder here of radius A. Okay, this is say r equal to A, or let us put it here, r is A. Okay, this is the radius. Okay. Now, we need to integrate over the surface. So, the only independent variable here is actually theta. So, we can take at an angle theta, okay, a small segment of elemental distance d theta. So, this angular distance here is d theta. Okay. So, we take a small element which has the angular increment of d theta. So, the length of this element is actually this length, which maybe I can do by a different color. This length is actually a d theta, because a is the radius of the circle or of the cylinder, right. More importantly, the pressure actually acts on this surface inwards. So, there is pressure acting inwards. Okay. The normal vector at this point on this surface is opposite, which is the unit normal n cap, it is acting outwards. What we need to do to calculate this force is to integrate, or is to write F, which is, let me say, force per unit depth of the cylinder. This will be the surface integral of minus P, which is the pressure, n cap, which is where it is acting, along that direction it is acting, into the elemental distance or the length of the element, which is a d theta, and we have to integrate this over theta from 0 to 2 pi. So, we go all the way around in the circle. So, if you could somehow figure out this integral, then we have our answer. Well, we use one more fact here, that since the element is at an angle of theta from the x axis, clearly the normal vector would also have components given by, for example, normal vector will have components such as cosine theta I cap plus sine theta j cap, knowing that the normal vector is a unit normal. So, it has a modulus of 1. So, we could write this as theta going from 0 to 2 pi minus P A, n cap is cosine theta I cap plus sine theta j cap d theta. This is the force per unit length acting on the cylinder. Okay. Now, we know the pressure distribution on the surface. Let us write this again on a fresh page. We know that the pressure distribution P on the surface is given as P naught plus half rho u square 1 minus 4 sine square theta minus 1 by 8 rho gamma square by pi square a square minus rho u gamma by pi a sine theta, right. Yeah, that is just to verify from the earlier expression, this is what we have. Okay, let me break this pressure distribution into two parts. Let me say this is part A. Okay, I am just going to call this as A, and maybe this is B. Okay. So, we need to put this pressure into this expression and then evaluate the integral. Now, instead of doing it the whole thing in one shot, I will do it in two parts. That is the reason I have written part A and part B here. Well, if you just look at part A, and if you were to calculate the force, let us say contribution, let us say from part A, F A, which would be integral 0 to 2 pi of, let us say, A contribution multiplied by A cosine theta I cap plus sine theta j cap d theta. So, if you were to integrate this function over 0 to 2 pi, you would actually get 0, and this I would like you to verify. Okay, this is a simple integral. I am sure you can work this out. So, I don't want to spend time basically deriving this trivial result. I am leaving this to you to prove. What I want to do is to show you what the B part gives, which is the second part of the problem. So, say we look at contribution on the force from the B segment of this expression, which would be 0 to 2 pi. We had a minus p, so minus p would become minus of minus rho u gamma by pi a sin theta, okay, times, say we will have a cosine theta I cap plus sin theta j cap d theta. Okay. So, just to make it a little simple, this negative sign cancels with this one, we have this a cancelling off with this one. What I will also do is I will split this, see, right, remember this force is a vector force. So, this will be force, for instance, along x. So, we could say this would be the component along x I cap plus some component along y j cap. So, what I will do is I will split the integral on the right side into two parts, where we just look at the x component and the y component. So, for instance, if I look at f x, that would be given as integral rho u gamma by pi, we will have a sin theta cosine theta d theta, right. That would be because the x part would come from this contribution, right, the coefficient multiplied by cosine theta I cap. So, we can evaluate this integral now very quickly. This would be rho u gamma are constant. So, they come out of the integral, we have pi anyway being a constant, we have just integral 0 to 2 pi sin theta cosine theta d theta, and I note now that if sin theta is my function, then cosine theta d theta is its derivative. So, this integral is quite easy to evaluate. We will just have rho u gamma by pi times sin square theta by 2 as the integral, which is evaluated between 0 and 2 pi. And now I note that sin theta at 2 pi is also 0 and sin theta at 0 is also 0. So, we get a 0 here for this part. What this means is that for the problem that we are dealing with, there is no horizontal force. For flow over a cylinder with circulation, there is no horizontal force to be felt. Now, what about the vertical component F y? This will be rho u gamma by pi sin theta, we will have another sin theta d theta. And what we do is we can pull out rho u gamma by pi, we will have a sin square theta. So, I will just multiply and divide by 2 in the numerator denominator. So, we will have 2 sin square theta in the numerator. The reason for doing that is that 2 sin square theta can be written in terms of the cosine function, cosine 2 theta angle. So, I would write this as 0 to 2 pi 1 minus cosine 2 theta d theta, which is what is 2 sin square theta, and this is now easy to evaluate. So, we have rho u gamma by 2 pi, the integral will become theta minus sin 2 theta by 2 evaluated at 0 and 2 pi. So, let us do this. So, we have rho u gamma by 2 pi, theta will just become 2 pi, and now note that sin 2 theta add 2 pi and 0 is 0. So, we will just have 2 pi minus 0 and this 2 pi will cancel with this 2 pi. So, we get rho u gamma, right. That is the force per unit length along the vertical direction, vertical force, which I can say per unit length, or you want to put it as depth, it is also the same thing, depth of the cylinder. So, this is what I am going to call as lift L. Okay. So, we have reached a very powerful result. In fact, we have now derived that in this case the lift force is rho u gamma. There is a vertical force and it depends on the free stream velocity u, or the far field velocity, and the circulation around the cylinder. Clearly, it also means that if the circulation was 0, the lift force would be 0, which is what we derived when we had just flow past a cylinder without any circulation. So, this result where lift is rho u gamma is called as a Kubakovsky theorem. And it is a powerful theorem because it is not just valid for, or it is not just the result, the outcome of the result of flow past a cylinder with circulation, it is actually true for any irrotation flow and around any arbitrarily shaped body. So, this result is applicable for 2D irrotational flow around any arbitrary shaped body, and that is why it is a theorem, that it says that the lift force around or the lift force generated by an object in a flow where there is some circulation would be given as rho u gamma. It is also applicable, for instance, you had a situation of flow past an airfoil, which is where the main purpose of deriving this law classically, or this theorem came in. If you had flow going over this airfoil, okay, so knowing the circulation around the airfoil, which maybe I can denote by gamma, and there is this velocity u, knowing the circulation around the airfoil, I could say that the lift force would be rho u gamma. That was the purpose or the utility of this theorem. Okay. So, any arbitrary shaped body, as long as there is some circulation, the lift force would be non-zero. So, this is what we did using the more classical approach, I would say. We derived the Kubakovsky theorem using the first principles approach by integrating the pressure distribution. We can also do this using the Blasius theorem. The same result can be derived using the Blasius theorem, and I will do it for the case of flow past a cylinder with circulation. Now, the Blasius theorem says that d minus I L is given as half iota rho times w square dz, where the integral is around the specific body that is under consideration. Now, in complex analysis, there is a well known theorem which is called as residue theorem, which is what we will use to evaluate this integral for our problem. If you are not familiar with this, or you do not recall what it is, I request you to go and look at it. Okay. So, I will quickly sort of give a description of what this theorem is, but the details I am deliberately not considering as part of this lecture series. So, how do we use this Blasius theorem? Now, recall that the complex potential in our problem for flow past a cylinder with circulation is u z plus a square by z plus iota gamma by 2 pi log of z by a. So, the complex velocity is w, which is df dz is u 1 minus a square by z plus iota gamma by 2 pi z. Okay. What we need in the residue theorem is a square of this velocity. So, we just square w. So, we say what is w square, which would be u 1 minus a square by, sorry, this should be z square plus I gamma by 2 pi z, this whole thing squared. So, let us expand this, we will get u square 1 minus a square by z square square, then we will have plus iota gamma by 2 pi z square plus 2 times u 1 minus a square by z square times iota gamma by 2 pi z, right. So, maybe 2 cancels here, we can expand these terms a little further. So, what we will say is we will get u square plus, when you open up this square, you will get u square plus u square by into a 4 by z 4 minus 2 u square a square by z square. The second term here I gamma by 2 pi z square will give you, iota square will become minus 1. So, we will have minus gamma square by 4 pi square z square, and this last one will actually give you imaginary terms. So, we will get an iota gamma u by pi z minus iota gamma u times a square by pi z cube, right. This is w square. Now, let us see where do we have to evaluate this integral. We have to evaluate that integral w square dz in the complex plane over the surface of this cylinder which has a radius a. Okay, we have trying to integrate it over in the complex plane, and the radius is a, and this is the contour C. Basically, the surface of the cylinder is the contour. Now, it contains this point z equal to 0, which is the origin. Z equal to 0 is also a point of singularity for this function w square. We say that it is singular because if you can see here now, there are specific terms where z equal to 0 makes this function undefined. Okay, so, it is not, the function is not defined, well defined. So, let us look at integral w square dz over this curve C, which contains a singularity, and this is where the residue theorem comes in. If we say this is integral I, then the residue theorem says that this integral I could be written as 2 pi iota times summation of all residues of the function w square inside this curve C. Okay, so, it talks about taking residues of this function inside this curve C, or whichever singularities exist inside curve C. Now, if we look at this function w square, right, it has different powers of z. It has negative powers of z. It also has a power of z to the power 0, for instance. So, I can say that this function w square is in the form of a Lorentz series. about the point z equal to 0, because it contains powers of z which are both positive and negative, okay, because it contains both negative and positive powers of z. The general form of a Lorentz series which is about z equal to 0 would be, for example, some function, I could say maybe g of z, some function, complex function, which is in our case is w square. The general way we could write this is in the form of, as I said, in the form of Lorentz series, which will have all possible powers, both negative and positive, and that would be a n, say z to the power n. So, that would be the Lorentz series typically that we could write. However, in our expression, I mean, it falls under the broad category of Lorentz series, except certain coefficients are only non-zero. For instance, we have a 0 to be non-zero, we have a minus 4 to be non-zero, we have a minus 2 to be non-zero, okay, a minus 1 to be non-zero, and a minus 3 to be non-zero. Only these are the non-zero coefficients in that series, the rest are all 0. Okay, if you just compare the series with this, which if you can put it in this form. So, to compute this integral I, the only term of significance for calculating this integral is the coefficient of the power z to the power minus 1. The coefficient of z to the power minus 1, which we are saying is a minus 1, for instance. Okay, this is the only number or only thing that we need to compute this integral I. For our case, we can write that d minus I L now, which was the definition of the drag force in the Blasius theorem right here, which is half I rho times the integral I is actually integral w squared dz, right. So, that is that integral that we would put up here. So, we need the integral I as I said is 2 pi I times the residues, and in this case we only look at coefficient a minus 1. So, coefficient a minus 1 is, if you look at the expansion here, okay, what is the number or the coefficient of z to the power minus 1? It is this number here, which is the coefficient of z to the power minus 1. So, this is a minus 1. So, we bring it here. So, we say that this would be 2 pi I times the residue, which is I u gamma by pi. This is residue of w square. Okay. So, we have I pi I gamma u by pi, which we put up here. Now, we can simplify this. So, this 2 cancels here, there is a pi which would cancel, and an iota will give you minus 1. So, we will get minus iota rho u gamma as d minus I L. So, we can compare both sides knowing that d and L are real valued numbers. So, clearly d must be 0, which is right. We have already shown that the x component of force is 0, and L is rho u gamma, which is again the Kubakovsky theorem. Right. So, we arrive back to the same result using a different approach, which is the Blasius theorem, and that is what I wanted to demonstrate by this method. Okay, thank you.